Benedikt, I've got a few questions for you. You'll be pleased to hear.
Of course.
The first question is about the commercialization. So is the method close to commercialization? Is it commercialized yet, and to what extent? And if not, how long do you think it might take to do that?
So with the current project which is going on, there might be a collaboration with the manufacturer of these acoustic cameras. So acoustic cameras are already available commercially and for different extents. However, they are commercially not used for buildings yet, as far as I know. So this combination is not commercially available yet. So this will be developed. I mean, the typical research project goes like 3 years or something. So it might be the goal is to commercialize this at the end in ETS with the manufacturers of these systems. I cannot say when this combination will commercially be available.
Okay.
But the subsystems are. Yeah.
Yes, thank you. So our next question asks then, so that the thermal image shows the leak. Is it affected by the outside ambient temperature or the temperature of the building materials?
It's affected by the temperature difference between inside and outside. However, it's of course affected if you have sun shining on the facade. It's very hard to because you have a very high temperature on the facade to really detect it, and it's affected by the material properties of the materials outside. So like emissivity and roughness, of course, as well. Like, yeah.
So is there an advantage to artificially increasing the delta T, perhaps, so that, for example, on a hot day, it might be advantageous to have cold air coming through the air leakage path?
Yes, of course. I mean, it's advantages. It's an advantage to do this during the heating period and in winter, of course. Then you have a large delta T. But the goal should be to develop a method which should be able to use throughout the whole year. So not only in winter, so you can go on site and what in summer or at the other period of the year. So this should be the goal.
So you presented some work on real buildings, which is always great to see. But it strikes me that there's some really quick wins, perhaps, with some laboratory-based tests on air leakage paths of known geometry. And so I was wondering if you could tell us a bit about whether this is done, and more interestingly, perhaps, about the responses you get to changes in geometry of air leakage paths.
Yeah, we actually did some measurements using acoustic measurements in a laboratory test setup. However, in this new possible project, there's the goal to really rebuild this and test both methods, so the infrared thermography method and the acoustic method within a new laboratory setup, to really be able to compare both methods or to within a controlled environment. However, we were able to see some changes with frequency and leak size, but this needs to be done more elaborated in the future. That's so yeah.
Okay, great. One question asks, could you do the test with the camera inside and the sound source outside?
Of course, yes, it's possible. So we did both. We had the feeling that it might be better if you would like to investigate more a larger part of the outside envelope if you put the camera outside. However, you have, of course, these disturbing sound sources outside, which you have not inside. So this is you can do both, basically, yes.
What's the largest area you can scan at one time?
Well, we can do the whole facade of the building at once. It depends. The measurement itself took only 4 seconds, so we only like the white noise signal was on for 4 seconds. That was enough for doing the measurement. But you have to, at that point, we moved the sound source from one room to another. So this is the thing. So you can leave the acoustic camera outside and then move the sound source from one room to another, and just for 4 seconds each room. So that's basically possible.
All right, so you're then just limited by the amount of time that it takes you to set up your equipment.
Yeah, I mean, at that point, when we did the measurement campaign, it took us longer because we repeated the measurements and everything, but basically the measurement itself was only 4 seconds.
Yeah, great.
Yeah.
Next question asks, have you tried to compare the results of the acoustic method in a room with a blower door test at all?
Yeah, we did it in a laboratory setup where we simulated the fan pressurization method and made acoustic measurements and tried to compare them for different kind of leaks using insulation material. In between, we created some artificial walls, like single walls, double walls with different kind of slits. And yeah, we're trying to estimate the amount of airflow at 50, 10, 4 Pascal with the fan pressurization method to the acoustic method, which was some kind of possible, but with a large error. So this needs some more elaboration to really quantify the leaks at that point, or getting the information about the geometry.
So I have a question here. I think it's not a question, it's more of a statement, which says, for thermography, consider using differential thermography.
Yeah, I mean, of course, we work on differential thermography and other kind of methods with thermography. We're thinking if it's possible to use it with or without a blower door. For differential thermography, you need a blower door.
Could you maybe explain to those who are unfamiliar with what it actually means? Could you?
Okay, I can. If you do a measurement of a facade without having a blower, or just a measurement of the facade, and then you turn on the blower door for overpressurization, so you have to force the cold air or warm air, whatever, going through the leaks, and then you make a difference between both measurements, and then you're seeing just what's the differential temperature, and then you see the leaks clearly at outside. However, for this, even you need some kind of temperature difference between 5 and 10 Kelvin, I think, or would be an advantage. And if you have sun outside, that's still difficult. So we're currently working on some. I gave a presentation at the last AIVC conference about this, about like some kind of login thermography where you can make turn on and off the blower door like 3-4 times on a regular frequency, and then you can see and you know the frequency, the leaks, the temperature at the leak changed at very small scale. And if you make a Fourier transform of the outside image, you can really detect only at very small frequency changes the leaks at that point. So this is we're trying to yeah.
Great.
Combine these things.
I can see that would help remove noise from things.
Indeed,
like
that's the case. The goal, indeed, yes.
Yeah. So two more questions. The first says that the Argonne National Laboratory has developed a somewhat similar acoustic imaging system that claims it can quantify leak locations, and there's a link for those who can see the screen to check out. Can your method determine the size of leaks? So that goes back to the geometry question, I think.
Indeed, yes. Yeah, I know the method from the Argonne National Lab. However, I've never been in contact with the colleagues from there, so I would be happy to discuss that with them. It is not yet reliably possible to determine the size. However, as I said, it's there are some indications that it's related to the wavelength and therefore the frequency of the sound source. So it might be possible, probably not to get the exact size in the future, but to the goal is to get some prioritization, so to say. Okay, these are probably the major leaks, these are the mid-size leaks, and these are probably the small leaks. We don't care at first place, to get some kind of, without saying, okay, this leak is like has an area of X square millimeter, whatever, but to saying, okay, these are large, mid-size, low. This it might be possible in the future, I think.
Okay, so there's a final comment before we move on to general questions. And so if anybody has any general questions, please could you start to add those to the chat now. And the final comment is from Barnard Bernard Hornen, who says, commends you on your presentation, says it's excellent. He says that he has successfully used ultrasound and advanced computer science to locate with microscopic accuracy air leaks as small as 0.06 millimeters in width, and by using algorithms to quantify the air flow rate through each individual air leakage path as small as 0.5 millimeter in width. So he says that he already has a commercialized tool and available in 120 countries. Maybe that's something worth checking out.
Yes, definitely. Thank you.
Okay, great. I'm gonna bring all the panelists back, so if you could all switch on your cameras, leave your microphones off until you talk, that would be great. I'm going to return. We didn't finish all the questions we had earlier on the pulse method. There's a question, some comments coming in. The first says that this method's been done before, perhaps in the 1980s, and so the question is asking for some clarification on the novelty.
Maybe I can touch on that. Can you hear me okay?
Yes, Ken, you sound great.
Oh, good. Sorry if we gave you the impression that we're trying to say this is a new method developed by us. Certainly that's not true. It's a method has been tried out by many organizations. I think, for example, Max Cerema tried it in 1986, and there are publications available. Rumor said he actually had a conversation with our late David Esrich about it before. I think the main challenge was the accuracy was not good enough, and I think something new we tried is kind of a scientific approach. That is new because we try to use the quadratic equation to isolate the unsteady term. Then we're able to develop the optimal configuration. For instance, the kind of combination between tank size and orifice size. So we're able to achieve a minimum unsteady term, so we can make sure accuracy can be maintained. Hope that answers that question.
Yeah, great. I think there's also a point to make. I'm not aware of another commercialized system that uses this method. So no. That's a pretty key difference. So although the physics may not be necessarily new, it's certainly new that it's a commercialized system that's been accepted certainly by UK building regulations. Next question then is, with a low pressure method, I wonder if you could comment on the non-homogeneity of pressure in large buildings and how that might be significant. I think the questioner here might be thinking of a large space like a gymnasium or a theatre.
Yeah, I can take that.
Oh. I was just going to say, Luke, I think earlier we touched on the fact that you can daisy chain pulse units around a building, so we can more fairly, I guess, distribute that air release. Certainly with large buildings, this was sort of, as I said at the beginning, the motivation behind the research. But of course, with testing sizes and the market, not least the market, sort of pushing us towards where we are now with the residential kit. That's not to say, however, more testing, more research needs to be done in the more cavernous buildings. And some of the work we did, or Ed Cooper did, in fact, back in 2011 in Sweden, where 7 of the piston units were used in a large cavernous area, which was, it was a church, and that gave good repeatability. But yeah, no, absolutely. Take the point that the sort of the large buildings is an area that we would like to do a lot more work on.
Great. So we know there are then limits, physical limits to volume. Are there environmental limits on wind speed and temperature differences? They certainly exist for the blower door test. How do they relate to pulse?
Certainly take this from the sort of product manufacturer perspective. Yeah, generally just with the blower door fan, as a general rule, calmer conditions are better, of course. So as a sort of the ideal scenario is wind speed of 6 meters per second or less, sort of 20 kilometers per hour winds. But that's not to say, and I know, Ken and Chris have been involved in a lot more research around this, that given the short nature of pulse, like the quasi-steady period is only 0.6 or so of a second, and the fact that you don't have any pressure tappings, so you're not penetrating the building envelope, you're kind of sheltered within the building itself. The method is also quite resilient to gusting conditions and things, and with experience you can work in and around more gusty conditions than those kind of 6 meters per second or so.
But that experience is an interesting point. Maybe I'll open that up to all three panelists, all three technologies, those representing all three technologies, when I ask this question, because I'm interested in how susceptible the test is to influence by the person doing the measurements. And maybe all three technologies could comment on that, starting with Nick.
Yeah. First, the person, but I also like to comment on the wind thing. Since the reference vessel is inside the house, and if you are in a relatively tight house, you can do excellent measurements even with quite some wind, although you're not then you of course get some delta P effect of lee and lee side effects. But we did in a passive house, we did at a really Beaufort 7 a measurement that was later repeated by blower door and gave very similar results. And then to the person doing it, well, you can't, this is something for like the blower door measurement, probably also whatever measurement you do, you need to be trained. And you need to be understanding what you are doing. So with the blower door test and with our test, you have to prepare the house according to the rules that are set for this kind of testing. You have to close the mailbox, etc. You have to. So yeah, there is some influence for sure.
Sure. And in that sense, it's no different to the blower door test because they all need to be sealed up too.
No, by all means, it's the same.
Have others tried to repeat your tests?
Yes, absolutely. We have at least sold a few of the units in the Netherlands, and there is a nice little movie on YouTube from The Hague. They have the municipality has bought an ATT, and the guy working there has done a lot of apartments with mechanical ventilation systems from those apartments, and some of them he did with blower door, and he did a lot of them with the ATT, and he had no problem at all doing this.
Thank you. Benedikt, has anyone tried to repeat your measurements?
No, but it would be great. No, therefore, I mean, it's not commercially available in this combination, so that's probably the reason at that point compared to the others.
Different researchers doing different elements of I wonder whether maybe you'd observe different things on different days.
I mean, especially for the infrared measurements, that there are different results for different days. So we're trying to minimize the error there at that point. But we had some issues. For example, at this very large building complex, I tried to explain there were at some points some harvesters going next to it and harvesting the fields. And that was then we have some like different results because it was very, very, very noisy. So we need to repeat something. So were some experiences we had at that point.
That's interesting. Pulse.
Yeah, I'd guess we're a little bit further down the track than the other two methods. We've had this on the market now for a couple of years. So there are about 120, 130 pulse kits in operation in hand in other people's hands. Generally, yeah, the equipment's remarkably simple to operate and use. In our training, the bit that we cover off, the highest risk, I would say, is actually how the operative measures the building volume and envelope area. So the volume being a function of the test, you get that wrong, and no matter how much work you put into the accuracy of all the instrumentation and the sensors, getting the meters cubed out by a percentage is probably your biggest risk. So yeah, quite a simple self-contained unit that's proven itself to be quite resilient.
I think we've got 1 minute left, and what we've identified today is we have 3 different test methods that are very different technology readiness levels. And Nick's clearly highlighted struggles he's having to get his technology recognised, and Benedikt, no doubt down the line, will have to face these points too. I wonder whether Luke, you could, and Chris and Ken, you could share the benefits of your experience and how you overcame the most significant hurdles to have the technology accepted by the UK government.
Yeah, we bear the scars. I had hair before I embarked on the whole Pulse journey. Don't get me right, it's been a real challenge, and obviously the air tightness testing in the round is a great thing to be doing, and I think everyone on this webinar will be of that view, and we should be testing more buildings. Every building should have an air tightness test, and so it's really exciting that there's some great innovation out there, but it's not easy when you've got the incumbent blower door fan, as you touched on at the start, Ben, that's been around 30-40 odd years, and that's, dare I say it, had a relatively easy ride. It's been kind of the only show in town and established itself in these international standards and things. And so, yeah, we've had to really raise the bar, and I feel like, I don't want to speak out of turn, the level of testing, verification, comparisons with other methods that we've done, the number of papers that are out there on the Pulse technique, it's kind of, it gives the blower door a run for its money, I think. There's still, it seems early days to having conversation the issues of repeatability with the blower door, or where it's susceptible to certain environmental conditions. So actually only by having these new methods come in do you then have a means of comparison. And it's slow, time consuming, hard work, and there's no substitute for lots of field work and validation, and finding the right people to speak to, the right stakeholders in government, and governments with the right attitudes towards innovation, I guess.
Well, thanks very much for your thoughts, and I'd like to thank our panelists very much indeed for sharing the benefits of their knowledge and their experience, and wish them very well with their future work. We'd like you to complete our survey to let us know how we've done on this webinar, which will come to you as you close WebEx. I'd also really encourage you to join us at the next AIVC conference, which will be on the 4th and 5th of October this year in Copenhagen, and we will have an air tightness stream, and so you will meet many of our speakers there if you wish to do so, and we'll spend 2 days talking about air tightness non-stop. So what could be a better incentive than to come to Copenhagen on the 4th and 5th of October? Until then, though, I wish you a very good day, and thank you very much indeed for joining us.
Yeah, thanks a lot.
Thank you.
Thank you so much.
Thank you, Ben.
Thank you.